Now we move on to a technical talk by Daniele Rossi, who's a professor at University of Pisa, and I'm going to let him introduce himself. I actually don't have the words here, so thank you and welcome.
Thank you. Thank you. Thanks. Oh, by the way, the screen down here doesn't work anymore, and from here I cannot see the big screen, and I have to use these mics. So can you please try and fix it? Sorry? No, the screen down there is not working, yeah. Yeah, in the meantime, I'm going to introduce myself. So, I'm Daniele Rossi, I'm from the University of Pisa. I'm teaching electronics there, and I've been working on RAS, which is going to be the main topic of my talk for several years now. So, anyway, I can do this probably. Yeah. Okay, thanks. So I'm going to talk about the hardware-software interface for RAS in the RISC-V. Okay, now thanks. RISC-V architectures, a piece of work that we have done within the EPI SGA2 project. And before moving on, I'd like to acknowledge my colleagues, Stefano Di Matteo and Sergio Saponara from the University of Pisa. And first of all, one of our students, Nikazu, who actually did the hard work. So background, so some brief outline. I will start with some background on RAS, the overview on the architecture that we have designed, and then some results about the verification and synthesis, and the test environment that we have implemented on an FPGA board, and then some conclusive remarks. So what we expect from a computing system usually is that it works with a very high performance, it consumes very low power, and we assume that it works properly over time. So we take this for granted often, but unfortunately that's not always the case. So, and techniques able to guarantee that a system works properly even in presence of errors do not come for free, unfortunately. So RAS, the acronym RAS refers to 3 different flavors of the ability of a system to perform the correct operation over time. Reliability, so the probability that a system produces a correct output over time. The availability, so it's the probability that the system is always available to provide the entire service. And serviceability, which is kind of measured at the time it takes for a system to be maintained and serviced. Also taking advantage of the information provided by the system itself. So in order to improve the reliability of a system, and we need to embed some kind of error control code in our system, especially if we are dealing with blocks that are more prone to errors like memories, for instance. So, but on top of this, also the hardware-software interface for error logging and reporting plays a vital role in guaranteeing a good level of the system RAS. Actually, it monitors the error messages coming from the error checking hardware implemented by the memories, and also provides the facilities to record, to store the information about this kind of errors. So providing a set of error register, memory mapped error register that are used to report in some cases, depending on what we want from them. I will clarify this later, to report the erroneous events to the system software. There are, of course, all main companies dealing with microprocessors are implementing these RAS features, Intel, AMD, or ARM. There's nothing yet about RISC-V architectures. There's a task group actually called RAS Error Report Interface or something like that, which is trying to develop the specs for this interface, for this peripheral, but there's nothing consolidated yet. So before going into detail about the hardware-software interface that we have developed, we need to go through some kind of error classifications. So we have an error, unfortunately. The error, and if we implement some kind of error control coding techniques, error can be detected. If they are undetected, unfortunately, we cannot do much about that. If an error is detected, we can correct it. If, let's say, the number of errors is within the correctionability of the error control coding. But we can also have uncorrected errors, unfortunately. For instance, if we have a single error correction, double error detecting code, so if we have double errors, we can just detect this kind of errors, but not correct it. In this case, if the data that is, let's say, affected by this error is going to be consumed by our system, we need to, let's say, we need the system software takes action to tackle it. So we need to, let's say, provide some error reporting to the system software. And these kind of errors are usually classified as urgent errors. But if errors affect a bunch of data that are not going to be consumed by the system immediately, we don't need to handle this kind of events immediately, so we can classify these errors as deferred. So, and deferred means that these data are kind of poison data, and as soon as, and when, and if this data is going to be consumed by the system, this deferred error will need to be escalated to urgent error and then properly handled by system software. And of course, the severity of this error increases when we move from corrected error to urgent error. So we have developed this RAS peripheral that includes several blocks. First of all, let's start with the error max that takes the control signal provided by the error checking hardware, and then, let's say, combine them properly, and then provides as an output the error message that includes an error code source which identifies the block generating the erroneous data, and then also the error type according to the classification that we have seen before, so either corrected or deferred or urgent. And this error message needs to be properly paired with the address of the location, including the erroneous data. Okay? And this message then is stored in a kind of FIFO buffer, which provides some ability, let's say, buffering and queuing ability. Then we need to properly store this error message within our set of memory mapped registers. And this is the task performed by this main controller, which selects where to, let's say, record this error message together with the address. And in this case, we have assumed that it behaves like a fully associative cache memory. So it selects basically the first location that it finds available. But in case all the error records are already occupied by a valid error message, it needs to decide whether to override the previous error messages or to drop the new error message according to the severity ranking that we have seen before. Then we have the deferred error controller that is able to handle properly the access of a deferred error, actually. Indeed, if we are accessing a deferred error location during a read operation, this means that the deferred error is going to be consumed by our system, so we need to escalate it to, let's say, an urgent error, and the system software needs to take action in order to deal with it. Whereas if it is accessed during a write operation, this means that we are going to override the location where the deferred error is. And so in this case, we can just invalidate the error record for this deferred error. So, and this is the set of our memory map error banks. that are logging the information about these errors. So let's go through them. So we have a feature register that is, let's say, configured at the implementation stage, which defines the main properties of our RAS interface. So what kind of errors we want to log, what kind of errors are going to produce, let's say, an interrupt request. So are going to ask for the help of a system software. Then, whereas the control register includes a set of enabling bits that can, let's say, either enable or disable the features provided by our system and described in the feature register. Then we have the error status register, which includes the main information about the errors and then the address. As I mentioned, that includes the address of the location into, where the erroneous data are stored. Finally, we have a couple of counters that are used to count corrected errors. Actually, if we think about corrected errors, we don't need to do much about them because they are corrected in hardware. So we could just ignore them. But for statistical purposes, it could be fine to at least to know how many corrected errors we have in our memories. And then we can also decide to log the timestamp of the errors that have occurred. Finally, we have the request generator that in case of an urgent error, so ask for the help of a system software to take action. We have synthesized our interface with this configuration, just 2 error record bands, which is the minimum number of error record bands that allows us to validate completely our interface. Both the corrected error counters, we have implemented both of them, a timestamp, 32 bits, the address, and the 4 entries FIFO buffer, then an AXI4 interface to allow us, so the processor to access the error record stored in our memory map registers. Oops. Okay, here it is. So some results about our standard cell implementation. We have synthesized it using standard cells and an FPGA, Xilinx Zinc Ultrascale platform. And what we can see about our, results, that the 2 blocks requiring larger amount of area are, of course, the error record banks and the FIFO buffer. As for the error record banks, we can say that if we want to increase the amount of, of errors that we want to log and be able to report to system software, we need to expand it, of course. And this area increases linearly with the amount of information that we want to store. Then we have developed a test environment on an FPGA, considering 32 RISC-V processor, but let me say that this architecture is not limited to be adopted in a 32-bit RISC-V. It can be also adopted in 64 bits. Then we have, and this processor is executing some precompiled C code stored in the main block RAM. Then we have 2 additional block RAMs, each of them protected by a single error correcting double error detecting codes that allows us to monitor what's going on in these RAMs and log the information about possible errors and report this information to system software. So we have error monitoring, error logging, error reporting, and also we have, of course, for testing purposes, we have implemented also some features about error injection. And this way we have been able to, validate the operation of our RAS interface for all the possible events that can affect our monitor memories in this case. So to conclude, we have designed this hardware-software interface for a RISC-V architecture. We have verified and validated it with an FPGA-based test platform. One of the main, let's say, advantages of this architecture is that it's highly configurable at implementation stage, and this allows us to have some flexibility about the area occupation that is mainly due to the error record banks that we need to consider. And as far as the frequency is concerned, we have verified that it's not, a limiting factor for the frequency that current processors are working at. So thanks very much for your attention. Okay, hopefully, okay.
Since it's a technical talk, we do have the ability to ask some questions. There's some microphones here.
And by the way,
Just like for one or two.
yeah, let me, I'm also the poster meeting room down there, so if you have questions, you can just come there and see me, but I'm available for questions now as well.
Anybody? The questions are between you, everybody at lunch. So,
Okay, yeah.
So I guess we're going to go to lunch, but there's one more slide that we're supposed to put up.
Yes, there was one slide on. Okay, thank you.
So I think maybe we don't have it yet, but just as a hint, we have also talks in the demo theater starting at 1 p.m. So if you look into the program, you will see during the lunch breaks, there will be some talks in the demo theater. That's in the hall, which is right, when you go this hallway down to the right, there's one of the exhibitions halls, and there will be happening. Okay, then enjoy lunch, everyone.
Yeah, so just, again, the demos are in the demo theater, but also please take the time and go take a look at the expo, because there's some great booths there, great posters there, so people took the time to make them. I think they're very interesting. So enjoy lunch. Thank you. We'll see you in a little while.
I can call you Betty, Betty.